Assalamualaikum. This video is part of the video pack series intended for ELE424 and Electronics 1. Hello, so we are continuing our video. We started off with the previous slides that explain the course outline and the lecture plans. So today we're going to start with the first topic, Semiconductor Materials, and this video comes with the slides Semiconductor Materials Set 1. I am Wan Fazlida Hanim Abdullah. I'm from the Faculty of Electrical Engineering, UiTM. So before we start, maybe it's good to have an overview of where we are in the scheme of things of the syllabus. So the syllabus has 9 topics, or rather is actually just 3 major devices, but how the course outline, the lesson plan is divided is that there are 9 topics. So we are here today first looking at the materials itself. Okay, so the other 3 devices that you'll be looking at in the future is the diode, the BJT, and the MOSFET. Again, as I said earlier in the previous lecture, this course is a very introductory course, introducing you to the basic semiconductor devices that are used in simple amplifiers. So but before we can look at the devices, we'll have to look at the semiconductor materials, and today is the video pack for semiconductors video 1, and we will be covering intrinsic and extrinsic semiconductors. So this is the reading list from references. You can have 3, Bolstad, Cedra, or Neyman. You can have a look later. So these are the topics that we'll cover. We'll start off with introduction. For introduction, we'll be covering some kind of background on semiconductors. Okay, and then we'll go to intrinsic semiconductors. Sorry, intrinsic is referring to the pure semiconductor material itself, producing charge carriers that are coming from the pure material itself. And then we'll go on to extrinsic semiconductor, where we will be introducing impurities and donors to the intrinsic semiconductor to produce, to change the concentration of the carrier in the material. Okay, so this would be with impurities, and then you'll be making the material either p-type or n-type. And then we'll finish off with drift and diffusion currents, where we'll be making the carriers move, because when carriers do not move, they're just carriers, they're not current yet. But there are some these 2 major processes, that is drift and diffusion, that will cause the carriers to produce currents. Introduction, background. So semiconductor devices from its invention has progressed a lot. Electrical switching and amplification has evolved from cathode ray tubes to transistors. So cathode ray tubes were designed somewhere around early 1900s, and transistors were invented somewhere around 1940s. So transistors are devices made of semiconductors, and this is what we're going to study, which are the devices that have evolved from this invention. So these devices have evolved following the trend of miniaturization. Miniaturization refers to making the devices small. Okay, miniaturization that allows huge amount of semiconductor devices on a common substrate. So meaning that on the same piece of material, which is usually silicon, you can have many from hundreds to thousands to hundreds of thousands onto a single substrate and package in one single package, and this is what you call integrated circuit. So for us as an end user, the devices are now fabricated and packaged in many forms for end users based on their needs and what they want to do. So sometimes they are individually packaged, or sometimes they are in the form of integrated circuits. So this is a picture of a real diode, and this is MOSFET. These are just examples. There are many forms of packaging, and then there is this bipolar junction transistor. So this is how they're going to look like. This is how the devices actually look like. But when we do our designs, when I would do our calculation, they will be represented in the form of symbols. So these are different kind of packaging that packages circuits, whether it is small or large or very large scale integrated circuits with all the transistors all in one pack. So these are just examples of how the thing would look like. Okay, so the top part are discrete devices, and this one here are discrete devices. If I can find my pen, yeah, okay, these are discrete devices and these are integrated circuits here. So this course will deal with components that are primarily due to the action of semiconductors. So based on what you've studied from science in school, you have covered conductors, insulators, and now semiconductors. So if you want a material that always conducts, okay, for example, a metal, aluminium for example, then you have a good conductor. Or you want something that insulates, that will not allow current flow like a metal, okay, then you can have a material that is always insulating in action. So for example, rubber, okay. But now you have semiconductors. So why semiconductor? The reason is because you can actually change the carrier concentration of the material through fabrication techniques by introducing impurities, and then you can make them have switching action as well as amplification action based on the voltages that you apply, because you are able to change different parts of the device's concentration. So first we'll have a look at intrinsic semiconductors, and before we have a look at that, let's look at semiconductor materials based on their group from the point of view of periodic table. Okay, semiconductor materials are either elemental semiconductors, which are usually group 4. So for electronic devices, the common ones are germanium and silicon. Germanium, historically, germanium is the first material that found its in the innovation history, but it has it's very sensitive to temperature. So silicon was then found to have better temperature sensitivity, and it has matured. So silicon is the leading semiconductor material for electronics now. Even though germanium devices still exist, but silicon is the material that dominates. And then other than elemental semiconductors, you have compound semiconductors, which are 3,5, such as gallium arsenide, gallium phosphide, and then you have 2,6, like zinc oxide. So intrinsic materials are semiconductors that are pure and do not have dopant added. In intrinsic materials, impurities that exist are not intentional and are at very low concentrations, meaning that if this is silicon, you only have silicon atoms in the structure, and even if you have impurities, they are not intentional. It's just impurities that are there, but actually you don't want it. Okay, so to describe semiconductors, okay, whether it is intrinsic or extrinsic in the future, there are two ways to describe the behavior of semiconductor carriers. First is the bonding model, and bonding model describes in terms of bonding of electrons, and energy band model, which describes in terms of energy bands that has valence band and conduction band. So this is just a revision. I think you've done this in your basic chemistry or physics subjects. So atomic structure and covalent bonding. In an atomic structure of a semiconductor, the outermost shell typically have 4 valence electrons because they're group 4. So for simplicity and relevance sake, we'll talk about silicon. So in the theory of atoms, the outer shell of silicon are allowed 8 states, but the outer shell of silicon only has 4. So silicon atoms form covalent bonding so that each atom has 8 electrons in the outer shell. Okay, so this is just a single atom. Now if I click the slide, now I have a single atom silicon sharing. The silicon atom has 4 electrons and it shares with 4 other electrons, making it 8 electrons. So this is the bonding model of an intrinsic silicon material. Silicon intrinsic material covalent bonding would have 8 electrons shared. So any electrons freed from sharing, okay, is due to absorbing sufficient kinetic energy from the natural environment, such as heat. So these electrons here, okay, they can be freed, and they can be freed just by absorbing sufficient kinetic energy from heat, from natural environment. So electrons freed from covalent bonding are carriers. These are what you call carriers. Free electrons are carriers, but valence electrons are not. So this these electrons around here, if they are still in the covalent bonding structure, they are called valence electrons and they are not considered carriers. But if one of these receives if the structure receives sufficient kinetic energy from the natural environment, and this one becomes free and it frees itself into the structure, then it becomes carriers. Okay, so when the electrons are freed, the electrons will leave an empty state, and when there is an empty state, okay, electrons in the nearby shared area will move to fill that empty state, and when this electron moves to that empty state, this causes an empty state, and when this electron moves to that empty state, this causes an empty state. So it's like an empty state that moves, and when the empty state moves, because it is filled by nearby valence electrons, it is called a hold. So here we see that there are two carriers that are formed. One is the electrons that are freed, and another is the empty state that moves. Okay, now leaving the bonding model, going to the energy band model. Okay, this is an energy model. It states that electrons can only have fixed allowable energy levels. In between the level is energy gap. So if you have an atom, I'm going to go back to this previous slide. Okay, this is an atomic structure of a single atom that is used in the covalent bonding, in the bonding model. So now instead of depicting that atom looking like that, we will now show it looking like this. Okay, so you have from the nucleus to the higher level, third level, second level, to the valence level. So electrons can only have fixed allowable energy levels. In between the levels is energy gap. So you look at this diagram, it focuses on the energy rather than the location of the electron. So the farther the electrons are from nucleus, the higher the energy of the electron. So energy in the second level have more energy than the third level. Energy in the valence level have higher energy than the second level. So the electrons at the outermost shell is called the valence electrons. Electrons that takes part in covalent bonding are valence electrons. The ones that you see before this, where you have okay, this one. So these electrons here that you see, these are all valence electrons. Okay, and again we know that valence electrons are not carriers because they are still participating in the sharing. So electrons that takes part in covalent bonding are valence electrons, but when they are free from the valence level, it goes higher, then it becomes carrier. So the unit here is what the unit of the energy, because this is like a diagram. All right, so this is like a y-axis. So the energy here, the unit is electron volt, eV. So when atoms are closer together, the levels now become bands. So initially what I showed you just now when I went back was a single atomic structure. This is also a single energy band showing separate energy levels, but when you have the atoms closer together, the levels now become bands, and this is how it looks like. We have ignored the second and third level. We only have the valence level showing the top part, this one here. This was the top valence band. So valence electrons bound to the atomic structure are shown in the valence band. So above the valence band is what you call the conduction band. So this was not shown just now. I can't find my pen. Okay. Alright, there it is. Okay, so this is the conduction band. So valence electrons, which are electrons in the valence band, they are not free electrons, therefore not carriers. But electrons in the conduction band are carriers. These are carriers here. So the amount of energy that a valence electron must have in order to jump from the valence band to the conduction band is called the ionization energy. This one. Okay. So when an electron leaves the valence band, an empty state is then created in the valence band. So when these electrons here leaves the conduction band, means that it is able to jump across this gap, this energy gap, sorry, okay, this energy gap. Now when the valence, when the electrons goes into the conduction band, an electron is formed, but it will then leave an empty state in the valence band. Now an empty state in a valence band is called a hole. Okay, holes in valence band are carriers, electrons in conduction band are carriers. Here electrons in conduction band are carriers, here holes in valence band are carriers. Holes are positive charge carriers and electrons are negative charge carriers. Okay, so before I leave this slide, this is just to emphasize that if you have electrons in the valence band, electrons that exist in the valence band, they are not carriers. Okay, electrons only become carriers when they enter the conduction band. Okay, this is the description that the energy band model puts. Electrons in the valence band are not carriers, electrons in the conduction band are carriers. Likewise, empty states in the conduction band are not carriers, empty states in the valence band are carriers. So empty states in the valence band are formed because the electrons have traveled from the valence band, overcoming the energy gap into the conduction band. Okay, so every time there is an electron carrier formed, a hole is also formed. Okay, now let's compare conductance of insulators, semiconductors and conductors. Okay, so the energy gap difference between insulator, semiconductor and conductor explains the difference in conductance. Okay, this is how energy band model describes it. If it's an insulator, the energy gap is wide. So because it's wide, electrons from the valence band needs to absorb a lot of energy to travel from valence band to conduction band to overcome the energy gap. Okay, so if it is if the energy gap is large, it's going to be difficult for the electrons to jump to the conduction band, meaning that there are not many carriers in the conduction band. Now for conductor, okay, you may have the bands overlap, so you just have abundance of carriers in the conduction band, which means that you have abundance of carriers. Okay, now for semiconductors, the energy gap is somewhere in the middle. Okay, oops. For silicon, for example, energy gap is 1.1 electron volts, germanium is 0.67, and gallium arsenide, for example, is 1.41. Intrinsic carriers. So wrapping up for these intrinsic semiconductor, for an example here, intrinsic carrier concentration of silicon is 1.5 times 10 to the power of 10 per centimeter cube, meaning there are 1.5 times 10 to the power of 10 of electrons that are free to move, electrons that have released itself from the shared bonding model in each centimeter cube. So intrinsic carriers refer to electrons and holes again that are created by the pure semiconductor structure itself, not due to the added impurities. So this value here are all electrons that came from silicon itself. So in an intrinsic silicon, free electrons only comes from silicon atoms. Okay, so holes are caused by valence electrons of silicon itself being freed, leaving an empty state, and moves because of nearby valence electrons occupying the space. We are now ready to go on to the next section, which is extrinsic semiconductors. So when does an intrinsic material become extrinsic? So intrinsic materials are pure materials. If the material is intrinsic silicon, then only silicon atoms exist in the crystal structure. We know that intrinsic carrier concentration from the previous slide is 1.5 times 10 to the power of 10 centimeter cube. This carrier concentration determines the conductance of the material. If you change the carrier concentration, you can change the conductance. So carrier concentration can be changed by introducing impurities called doping. Okay, when the material is doped, it is not intrinsic anymore because you've already intentionally introduced an impurity. The semiconductor is now extrinsic. So it becomes either N-type or P-type depending on the type of dopant that you have introduced. So N-type. Now I'm going to explain this using bonding model first. So impurities, meaning that a material that is different from the semiconductor material with 5 valence electrons or pentavalent are called donor atoms, or group 5. They come from group 5. So here we have an example of a silicon material, and antimony Sb is introduced, and antimony has 5 electrons. So examples are antimony, arsenic, and phosphorus. So the 5th electron, because it has 5 electrons, the 5th electron is loosely bound and becomes free easily. And donors directly donate electrons that can easily become free. Okay, all these silicons, they have 4 electrons, but this one is easier because it is not actually participating in the covalent bonding sharing. So donors directly donate electrons and they can easily become free. So for a p-type, impurities with 3 electrons or trivalent are called acceptor atoms, and they come from group 3. So typical acceptors are boron, gallium, and indium. So here I have an example here of a silicon material with boron introduced. So boron have 3 electrons, and one of this location is void. Okay, so vacancy in the covalent bonding is called a hole. So for holes to flow, neighboring electrons fill the holes up, causing the holes to move. Okay, so they're like free moving positive charged. Okay, acceptor accepts electrons, causing a vacancy in the shared electron structure. So because of this void accepts electrons, and this valence electron would move to that area, this valence electron would be to move to that area. So a hole is created not because silicon valence electron is freed, but because of the void area that the acceptor atom introduces. So before I leave this slide, it is now, I think it has become apparent that every time a carrier electron is formed by freeing itself from the valence band, if it's in the energy band model, or from the bonding of the covalent bonding, an associated hole is also formed. So let's look at this explanation of N-type and P-type from energy band model. So doping with donor atoms introduces a donor level. So we know from our previous discussion that we have a valence band, okay, and we have a conduction band, and between the valence band and the conduction band is energy gap. So if an electron wants to become a carrier, it has to leave the valence band, okay, to go to the conduction band, and in order to do that, it has to overcome energy gap by absorbing sufficient energy from the environment. So what a donor does is that doping with donor atoms, it introduces a donor level. This is a donor level, okay, meaning electrons are allowed to exist at this level. It's actually in the energy gap, but because it has introduced an allowed energy level, and this level is close to the conduction band. So we know that donor atoms have 5 electrons, so this 5th electron, the donor, sits at the donor level, which is close to the conduction band. And if it is close to the conduction band, the electrons at the donor level can enter the conduction band easily and become carriers, because the condition for an electron to become carriers is that the electrons must exist in the conduction band. Whether it comes from the valence band or whether it comes from the donor level, it doesn't matter. As long as you have electrons in the conduction band, then you have carriers. So since it is closer, less energy is required, hence more carriers are created easily. Now these carriers are the extrinsic carriers. They are typically between 10 to the power of 12 to greater than maybe 10 to the power of 20 centimeter cube. Okay, compared to the intrinsic semiconductor carrier, which is 10 to the power of 10. So p-type, doping with acceptor atoms instead of donor atoms, if you do an acceptor atoms, what it does is that it also introduces an acceptor level, meaning electrons are now allowed to exist at this level. So in the energy gap, okay, in the energy gap, what it introduces is that it introduces a level that is close to the valence band. So the lack of the fourth electron that the acceptor has, what it does is that it creates this empty acceptor level. Okay, so it's an empty level. Okay, so the valence electrons in the valence band are close to the acceptor level, so valence electrons fill it up. Now valence electron going to the acceptor level does not make it a carrier, because for it to become a carrier it has to go to the conduction band. But what happens now is that when the valence electron leaves the valence band, okay, it leaves holes in the valence band, it leaves empty states in the valence band, therefore it creates holes there. So recall that energy band model states that vacancies in the valence band are holes and are considered positively charged carriers. So holes in p-type are easier to be formed because the acceptor level is close, allowing valence electrons to create vacancies in the valence band. The extrinsic acceptor hole concentration, like donor electron concentration, is also significantly larger than the intrinsic carrier concentration. So you have here a concept of majority carrier and minority carrier. N-type materials contain an excess of electrons. Because you have introduced donors, it has excess of carrier electrons. In N-type, electrons are majority carriers, and holes are minority carriers, and you would expect that the minority carriers are close to the intrinsic value. So p-type materials contains an excess of holes because of the introduction of acceptor atoms, and p-type holes are majority carriers and electrons are minority carriers. Okay, so you have n-type and you have p-type, depending on the impurity that you have introduced. Okay, so in an n-type you introduce donors, in p-type you introduce acceptors. Okay, in n-type the majority is electrons, okay, and in p-type the majority is holes. Okay, so now we are ready to go on to the next part, which is drift and diffusion current. So current is due to movement of carriers. Now, when an electron becomes a carrier and an associated hole is formed, it has not yet generated current. It is only when the carrier moves, there is a resultant motion of the carriers, then only it becomes current. Okay, so the creation of negatively charged electrons and positively charged holes in the semiconductor process produce charged particles. Now, charged particles are not yet current. These charged particles, electrons and holes, are referred to as carriers. Okay. If carriers move, current is generated. The two basic processes which cause electrons and holes to move in semiconductors are drift, okay, and diffusion. Drift is when the movement is caused by electric fields, meaning electric fields is the thing that makes the carriers move. But diffusion is the flow caused by variations in concentration that we call concentration gradients. So drift current, okay, this is also something that you've learned in science subjects earlier, but I'm just repeating this here. So when an electrical field is established in a semiconductor crystal, holes are accelerated in the direction of the electric field. Okay, if this is the electric field, let's start with there, electric field, holes are accelerated in the direction of electric field, and free electrons here are accelerated in the direction opposite to that of that electric field. So positive charge moves in the direction of positive electric field or positive current, and negative charge moves in the opposite direction of positive current, even though the currents are maybe most probably be formed because of electrons, but the direction of negative charge is in the opposite direction of positive current. So diffusion current. Now diffusion process, general diffusion process, not just for electrons but for any kind of atoms and molecules. Now in the diffusion process, particles flow from a region of high concentration to a region of lower concentration. So carrier diffusion occurs when the density of charge carriers in a piece of semiconductor is not uniform. So let's say in part of the semiconductor has a lot of holes, okay, and the other part does not have a lot of holes, it will naturally move. So if one side of the material has higher concentration than the other side, and carriers move from high concentration to low concentration, the current is generated, and it is called a diffusion current. Okay, so this is a diagram that we have here. Here we have a lot of holes, so you have high hole concentration with the associated graph below it, and here you have less hole concentration, so you have lower hole concentration here. So these holes will flow in the direction of the difference in the hole of concentration. So this is unlike drift current, because drift current moves because of electric field, but diffusion current moves because of the differences in concentration. So what's for the next lecture? When p-type and n-type are side by side, magic happens. So next topic is p-n junction. When p and n are side by side, there is a depletion region that exists at the boundary, and current will flow based on the nature of applied voltage between the two p-n terminals. Thank you.